Hello everyone. Welcome to the final session revision course for revision class for defects in crystalline solids part 1. This was an NPTEL 8-week course where we studied about crystalline solids, the defects in crystalline solids, how these defects in crystalline solids help in the enhancement of properties or decrement of properties. Then what are the defects? How these defects move inside the crystalline solid? We studied about that. The course coordinator for this course is Professor Shashank Shekhar, and I was the teaching assistant for this course. So this is a revision course for the revision class for the whole course, where I will be revising very briefly about the topics, major topics that we discussed. I will be solving some questions also as we proceed through this course, through this class. Sorry. Then finally, these discussions will be helpful for you to answer some of the questions in the assignment, and will be helpful to answer some of the questions in the exams. So let's begin the course. We started this course with defining crystallinity. What is crystallinity? Crystallinity is the periodic arrangement of atoms inside a solid. So based on this periodic arrangement, there are two types of solids. One is crystalline solids and another one is amorphous solids. In crystalline solids, we see periodic arrangement of atoms, where in amorphous solids, this periodic arrangement of atoms are not present. This is in two dimension. This figure is in two dimension. But as we increase the number of dimension, like as we go into the three dimension, we will be seeing the periodic arrangement of atoms in three dimensional. Whereas in case of amorphous solids, there will be no periodicity observed in three dimensions. Then we introduce the concept of defect, like what defect is. As we know, defined that in a crystalline solid, there is periodic arrangement of atoms, but in a defect, there will be a discontinuity in the periodic arrangement of atoms. This is known as a defect. So the example of a perfect crystal and the example of defects is shown here. And the defects are divided into various types, such as point defect, line defect, the three-dimensional defects, two-dimensional defects, surface defects. And based on this, there are various examples shown here. As you can see, this is a point defect where an atom is missing and a new atom is replaced by the atom. And here also, and this is creating a strain field around this periodic arrangement. Here it's the same. The atom size is larger and it is also creating a strain field. And there is a vacancy of atoms here. The atoms is not present. Then interstitial atoms is present. Then grain boundary, which is a surface defect. Edge dislocations. This is like a presence of an extra half plane. Then precipitations, pore inclusions. These are all different kinds of defects which are observing in case of solids. Then the classification of defects based on dimensionality, the defects are classified into 0 dimension, 1 dimension, 2 dimension, and 3 dimension. So mostly we will be discussing in this course about 0 dimension and 1 dimension defects, sorry, and the 2 dimension defects will be discussed much more in the second part of this course, which is in the next semester. So coming to the zero dimension defects, there are various types. There are various types such as vacancy, impurity, Frankel defect, and Schottky defect. So what are these defects? Let us see first. First, let us define what is point defect. Point defect or zero dimension defect. That means there is a defect at a particular atom site or particular lattice site. For example, interstitial atom, foreign atom is present in place of a lattice site. This is known as an interstitial atom or substitutional atom. The lattice position is replaced by a foreign atom, that is known as substitutional larger atom. Or can be that the lattice site is vacant, that the atom which should be present in the lattice site is absent. That is known as a vacancy defect. Then for ionic crystals, ionic solids, there is Frankel and Schottky defects observed, which I will be discussing much more as we progress through this lecture. There may be a question like how this, if we are keeping a crystal, directly there will be defects introduced in a crystal. It does not happen like that, right? So the generation of defects require a favorable energy, which will overcome the activation energy barrier and finally help in the defect production. And this favorable energy is provided by various methods, such as crystal growth, quenching, irradiations, and plastic deformations. These are the main reasons which provide the favorable energy for this defects, for the nucleation or the growth of the defects. Another thing about point defect is that, as I told you earlier, these are limited to a lattice site or a lattice point, and these are exactly 1 or 2 atomic diameters in size. But the effect which is felt is along long distances. It is very less. It's just a replace of an atom, but this effect is observed at a very large distance. Then we'll be discussing more about one of the zero dimension defect, that is vacancy defect. So what is happening in vacancy defect, as the name suggests, in there is a periodic arrangement of crystal, and one of the lattice site is vacant. One of the site is vacant, which hampers the periodic arrangement of crystals, periodic arrangement of crystals, because this lattice site is vacant, so the arrangement will not be proper. This is known as a vacancy defect. Then we used various mathematical derivations to find the fraction of mono vacancies and all, which is dependent upon the free energy change as well as the entropy. Then how to measure these vacancies, this concentration measurement, how to measure these vacancies? The first measurement technique is thermal expansion. In thermal expansion, what is happening? The volume of a material, we are expanding a material thermally with the help of heat. So the volume of the material increases, so there will be a change in dimension. This change in dimension can be used to find out the defects concentrations. This is given by n by n equals to 3 delta L by L. Delta L by L is the change in length by original length, which is measured optically by optical measurements such as microscopes, and delta A by A, change in lattice constants, which is which we get from XRD data. Then heat capacity. Heat capacity is given by this formula, which where we will be knowing everything except the Na values, which we can calculate the vacancy concentrations. Then there is another method known as positron annihilation spectroscopy, in which positron particles. What are positron particles? These are electron particles, but with a positive charge. We generally know that electrons should have a negative charge, but positron particles have a positive charge. And these are bombarded onto elements. And let's compare two situations where a sample has a very less amount of defect and the sample has more defects. So if a positron is bombarded onto the sample having less defects, what is the reason, what is the problem in that? If the defects are less, that means the electron density is more, because the defects are less, electrons are there present in the sample. So that means the positron which is bombarded onto that sample having less defects will be immediately annihilated or immediately decayed, because the electron density is more. This will give you the thing that there is a less amount of defects. The time of decay. Finally, the material having more defects. That means there has lower energy density. That means the decaying will be taking place at a very long period of time. The positron decaying, and this average time decay, the average decay time can be related to the vacancy concentrations. We can also measure the vacancies with the help of resistivity and conductivity too. Then there is another defect such as self-interstitial defect. Self-interstitial defect means first interstitial means there is a particle present at an interstitial site, and there is a term called self. That means the own in the own material, the own atom will be going and sitting to a going and sitting over a interstitial site. So as as the own material in the own material, its own atoms is shifting positions, there will be a vacancy created at the original site, and these atom moves towards a different site. So there will be a self-interstitial atom at a different site. So this in self-interstitial defects, it leads to the creation of a vacancy. Then it leads to the creation of a interstitial position where the self and material is present. Then we have Frenkel defect. As I told you earlier, the Frenkel defects and the Schottky defects are observed in case of ionic solids when there is a positive charge and negative charge. So in Frenkel defect, what happens? The cations, that is the positively charged elements, one of the site is absent and is present at a interstitial site. So this is self-interstitial defect, but in case of an ionic solid. So therefore, it is known as a Frenkel defect. The lattice point, the cation where the lattice point where the cation was present is vacant, and this cation goes into a different lattice points and takes an interstitial position. Then we discussed about Schottky defects. So what is a Schottky defect? Schottky defect in which a Schottky defect is also seen in ionic solids. In is what happens here? There is a absence of a positively charged element. Along with that, to balance the charge, there is an absence of a negatively charged element. So two lattice sites are vacant. One lattice site is positively charged lattice site is vacant, and the negatively charged lattice site is vacant. So this is just to show the comparative study between Schottky and Frenkel defects. What happens in case of Schottky and Frenkel defects? There is another defect known as anti-Frenkel defect. What happens in anti-Frenkel defect? The lattice positions, the atoms which are present, the as we told you earlier, the in case of Frenkel defect, the cations are absent in their lattice positions and sit in other places. When the anions do that, the anions, that is the negatively charged elements, do that, like they will be absent in their original site and going into the other interstitial sites. This is known as an anti-Frenkel defect. Then we studied about intrinsic and extrinsic defects. Like what are these? In intrinsic defects, as the name suggests, there is shifting of atoms in the interior. We, that is self-sufficient or self-interstitial kind of defects. So self-interstitial, Frenkel, Schottky, these are all intrinsic defects. There is no external addition of impurities. In case of extrinsic defect, as I told you, there will be an external foreign impurity or external addition of impurity at this at the lattice sites or at the interstitial positions. So as I told you earlier, it can be at lattice site or interstitial position. That means when it is at an interstitial position, it will be an interstitial extrinsic defect. And when it will be at a lattice site, it will be a substitutional defect because the lattice site will not be vacant, but it has to the element in the lattice site has to go out and new element has to sit there. This is known as substitutional defect. The difference between these two things are in interstitial extrinsic defects. These are easy to find and easy to move to the next sites because the interstitial sites are always vacant, right? There is no presence of atoms in the interstitial sites. But what happens? This is an interstitial site, the space is too constricted. So when you're trying to add any foreign element to that space, it will create a distortion around the site, which results in very large strains. Then comes to substitutional defects. In substitutional defects, these are not easy to find because all the lattice sites will be occupied by atoms, right? So to move to create the lattice site, what will be happening? We have to move that atom from that original lattice site. It has to go out of the sample or go to a different interstitial sites, and the foreign atom has to sit in that lattice site. So there is a lot of energy involved here to remove the atom, to make the atom sit in that, to make the foreign atom sit in that substitutional site. And the movement will not be easy because the substitution sites are not vacant, but the fitting will be easier as these are lattice points. The fitting will be easier, but still the strain exists in the sample because the size of the foreign atom is different, right? So it creates a small strain field around this lattice sites. Then we discussed about tetrahedral and octahedral voids. What are those? Tetrahedral voids, it looks like a tetrahedron. It looks like a tetrahedron. It is found by four atoms at four different vertices. Then what is octahedral site? Octahedral site, it looks like an octahedron where it is found by six different atoms. Then we discussed about where the octahedral and the tetrahedral sites are present in case of BCC and FCC material. Then we discussed the radius of the void and the radius of the atom ratio. Radius of void and radius of atom ratio in case of both FCC and BCC crystals in tetrahedral and octahedral voids. Then we discussed about defect reactions. Like these defect takes place, right? For one atom, as we are telling so clear, easily that one atom will be going from its original site to a different site, and foreign atom will be sitting in this space. This does not happen so easily. So to define these reactions, we have certain rules known as Kroger-Wink equations. And these rules include mass balance. There should be mass balance on both the LHS and RHS. There should be electroneutrality, that is, net effective charge will be constant. Electric neutrality should be present both on LHS and RHS. And the ratio of lattice sites should be maintained. Like if a vacancy is created, then there should be an interstitial atom present. The atom should not go anywhere else. The lattice ratio of lattice sites should be maintained. So this is just the defect reaction, how it is written. In Frenkel defect, strontium creates, what is Frenkel defect? In Frenkel defect, there is a missing of a positive atoms, and what happens? There is a missing of positive atoms in Frenkel defect, and these positive atoms are cations in the Frenkel defect, and these positively charged elements goes and sit to somewhere else. So this is aluminium. You can see what is the thing happening in aluminium? Oxygen. Then Schottky effect. In Schottky effect, what happens? A positive as well as a negative element is absent. So what is happening in a Schottky effect? You can see strontium vacancy is created and the alloy is formed. Then let's solve some of these questions. Actually, we have solved these questions before, but let's solve it again to give you a very brief idea of what is happening in case of Kroger-Wink notations. Schottky defect formation of MgO. What happens? We know that Mg is Mg plus 2, O minus 2. And Schottky defect. In Schottky defect, what is happening? There will be a positive atom missing and there will be a negative atom missing, both. So MgO will be giving, so Mg site is absent, a positive atom is absent, so Mg is plus 2. So there will be a vacancy at the Mg position with a negative charge, because well, there will be vacancy at the negative charge because the positive charge is gone from that position. Plus, along with that, oxygen is also missing, so there will be a vacancy at the oxygen side with two positive charges because oxygen has a negative charge. plus the Mg atom will be present at an interstitial site, or Mg atom will be present somewhere in the material. So there will be an Mg atom with two positive charges, plus there will be an oxygen atom with two negative charges. This is what is Schottky defect formation, which is at the surface, and this will be at the surface. The positions of these images will be, positions of these elements will be at the surfaces. Then there is a Frankel defect formation. What is Frankel defect? Frankel defect is like the positive charge cation is present, and that this cation goes and sits in the vacancy site. There is another interstitial site, right? So let's write the equation MgO. In Frankel, what will happen? There is a vacancy created at the Mg site because the Mg cation is going, and there will be a negative charge at the vacancy. And the magnesium which left the element will be going to an interstitial site where they will be having a positive charge. The interstitial site will be having a positive charge, and the oxygen will remain as oxygen because there is no movement of oxygen in case of a Frankel defect. This is what is this is what is Kroger-Wing notation tells us how to write the equations how to write the defect reactions. Then we studied about diffusion. So we defined diffusion in as previously what we have learned about diffusion. A material is going from lower concentration, a material is going from higher concentration to lower concentration. But sometimes a material also travels from lower concentration to higher concentration, and this is also termed as diffusion. So there is an ambiguity in this definition. So therefore, to define diffusion, we use the concept of chemical potential. What is chemical potential? Chemical potential is the energy associated with a unit quantity of a substance. So the diffusion is defined as a process in which a material is transformed from a higher chemical potential to a lower chemical potential. So there is a question like diffusion is a result of random motion of particles, of course, concentration gradient, of course, kinetic energy of the particles, of course, these three will be happening in case of diffusion. And there are types of diffusion in point defects. The types of diffusion in point defects are interstitial diffusion, like there is a diffusion within the interstitial site, and substitutional diffusion. And what is the difference between these two? The interstitial diffusion, the size is very small, and lesser disruption of elements takes place because the size is very small. Interstitial site and lesser disruption. But in a substitutional diffusion, what is happening? There is a size mismatch at a lattice point, and the lattice has to rearrange themselves, which requires higher activation energy. Then, as we defined diffusion, then we learned about Fick's laws of diffusion, where we learned about Fick's first law, Fick's second law. Fick's first law states that the flux at a steady state, the flux known as the flux is proportional to the concentration gradient, and the diffusion dependent upon the temperature because of the increased motion of the atoms. Then the Fick's second law relates the rate of change of concentration with time to concentration gradient in case of 2D, and in case of 3D we saw that. And there is a question like calculate the diffusion coefficient in solid at temperature equals to 800. So the temperature given is 800 Kelvin. D naught is given as a value of 50 meters square per second, and activation energy is given, EA is 10 joule. What is the formula for diffusion coefficient? Diffusion coefficient is given by d naught exponent minus delta minus ea upon rt. Here everything is defined. ea is defined, t is 800 kelvin, r is 8.314 as no we know. D naught is defined, so we can find out diffusion coefficient at 800 kelvin directly from this formula. Done, right? Then we studied about carburization. Carburization is also an process which takes place by diffusion. What is carburization? Where some materials do not have higher strength, so we are adding carbon to this material to show a property of higher strength. Just we are coating the surface of the material with carbon. And this coating of with carbon takes diffusion takes place within the material too, at the surface. And this diffusion is also can be defined as an error function value. This diffusion of carbon atoms from the surface to the interior of the atom is defined by C minus C naught by Cs minus C naught equals to this equation, 1 minus error function of x by 2 root dt, where C is the concentration at a particular amount of time. C naught is the initial concentration, Cs is the final concentration, C naught is the initial concentration, and D is the diffusion coefficient. X is the distance up to which the at which we are calculating the concentration, and T is the time. There is a question regarding this. Actually, we have solved this question previously. If you have any doubts, you can always go back to the solutions which I have done for this question. These questions are quite very easy. Just to you need to apply a small amount of techniques, a small amount of tricks to answer these questions. Then finally, we'll be coming to one-dimensional defects, that is line defects. Um, the first thing we'll be studying is dislocations, disclinations, and disparitions. These are examples of line defects. The Paul Oroyan and Pollyanna in 1934 were awarded with the theory of dislocations. They were credited with the theory of dislocations. They initially started the theory of dislocations. Before that, what was the theoretical strength? That means theoretical strength means that if the dislocations are nothing, if the materials are defect free, the yield stress of the material is given by G by 2 pi, which is quite high. G by is or G by 10. For steel, it comes out to be exceptionally high, which is never observed in case of steels theoretical strength. Therefore, it was concluded that there is some defects in the material, so the materials are not defect free. There are some defects in the materials which will be decreasing the strength of the theoretical strength or the any strength of the material, theoretical strength of the material. Sorry, yeah. Then we define the strength versus dislocation density graph. This is a crystal whisker, pure. There is no defects at this place. There is no defects, no defects in the material, and the dislocation density will be very less. That's why the strength is very high. And here the sample is annealed sample, where the strength will become low, but dislocation density is also a little bit higher. And finally, the sample 2, these are normal samples where the strength will be higher as well as the dislocation density is higher. Then this disclinations and dislocations, they are explained by Volterra model, where Volterra took a hemisphere, sorry, not a hemisphere, a hollow cylinder, and he divided this hollow cylinder into various ways. When he cut this hollow cylinder in a straight line, this is known as a dislocation. But when the hollow cylinder was cut at an angle, hollow cylinder was cut at an angle, this is known as disclinations. There are various explanations regarding this dislocations and disclinations. You can always go back to my presentations and Professor Prashashank's presentations to get an idea about that. But to discuss here, we are discussing here is that the dislocations according to Volterra model has a straight line or a straight cut on the hollow cylinder, whereas the disclinations has an angular cut. And the disclinations are very rare in case of materials, in case of metals. Sorry. So therefore, we'll be concentrating more on dislocations. There are the dislocations are of two types. One is edge and one is screw dislocation. Let's watch a YouTube video to just give you an idea of what is screw and edge dislocation. Just a second. Okay. Yeah, when you want to see the video, you can always go back to the. This is there is a mirror opening the video. So when you want, if you want to see the video, you can always go back to my previous presentations to have a look at these videos. And the mixture of these dislocations is like the edge and this screw dislocation when present at the same time. This is known as mixed dislocations. And in general, and in general, um, in materials there is always presence of mixed dislocations. The edge and screw dislocations are not purely present in the sample. Then the characteristics of dislocations, and the dislocations line must form a loop or a branch into other dislocations. The line dislocations may not change, but the Berger vector, the line direction may change, but the Berger vector will remain always constant, and the slip characteristics of Berger vector remains constant always. So there is a glide loop and prismatic loop, where the glide loop and prismatic loop, where there are multiple screw and behavior. This is the line vector. So this is the Berger vector. This is the Berger vector 2, where the Berger vector is this, the line vector is this. So this will be showing you edge character. Here also will be pure edge character, but here pure screw character, the pure screw character. But any other places, they will show you mixed character, edge and screw, edge and screw, edge and screw. But in prismatic loop, what is happening? Pure edge character is seen. The materials pure edge character is seen in the material in the loop. Then, with the help of elastic continuum model, we defined screw dislocations. We defined the stress and strains of screw dislocations, the stresses of screw dislocation, and the strains of screw dislocation, along which direction it is present. We also saw that. And one thing to note here is that the stress and the strain both are inversely proportional to R. So the R when tends to 0, the sigma value tends to infinity. So at the core of the dislocation, the stress is too high. It is infinity. Stress is too high at the core, or very near to the dislocations. So that's what we got an observation from. Then there is a question: given a screw dislocation with the following parameters, the Berger vector magnitude is given, the B is given, the shear modulus G is given, distance from the dislocation line D is given, angle is 45 degree. What is the shear stress component? The shear stress component is given by minus GB cos theta by 2 pi r. Right? This is r. This is r. Sorry. Minus GB cos theta by 2 pi r. So everything is given. G is given, B is given, theta is given, R is given. So we need to just find out the shear stress component of this. This is 1 and GB by 2 pi r. GB minus GB sin theta by 2 pi r will be the other one. We discussed about dislocations. Yeah, we discussed about these questions also previously. You can have a look at these questions. Total energy of the dislocation, how it varies depending upon this. Then image forces, we also defined what are image forces. Then finally we defined the motion of dislocations. The motion of dislocations happen in two ways. One is glide and one is climb. As you can see here, the glide and climb can occur both in edge and screw dislocations. As you can see here, in screw dislocation, the glide means it passes the movement of dislocation happens along the slip plane, on the slip plane or along the slip plane. As you can see here, in the edge dislocation, the movement of dislocation happens along the slip plane. This is the slip plane. The movement of dislocation happens along it. But in case of climb, what is happening? The movement is opposite or perpendicular to the slip direction or slip plane in case of climb. Similarly, in screw dislocation, the glide will be along the slip plane, whereas the climb will be perpendicular to the away from the slip plane. Glide and climb. This is how the motion dislocations move. Glide and climb mechanism. Then there's a question like determine whether the sodium is edge, screw, and mixed. Identify the slip plane and the dislocation line. We'll be calculating B dot L for to find out screw or L. If B dot L, B dot will be calculating B dot L, dot product of B dot L. So if B dot L is 90°, that is perpendicular, then it will be an edge character. If B dot L is 0°, that is along the B is along L, so it will be a screw character. And mixed character will be anything between 0 and 90°. Acute angle will be mixed character. But the moment of dislocation will not be so easy, right? There will be resistance to dislocation moment. This resistance is provided by the width of the core and the lattice resistance. The lattice points are always filled. So nobody wants to be replaced by a new lattice, right? So that's why the lattice also provides resistance to its original movement. And the width of the core, as we saw earlier, the force at the width of the stress at the width of the core is very less, very more large. It tends to infinity. So the width of the core is an important resistance to the dislocation motion. And we talked about slip planes, right? What are those systems? So the slip system is defined as the largest distance between the two planes, largest distance between planes, and the largest atomic density planes. This is known as a slip system. A slip system, like an how can we define what is a slip system? It should have a largest distance between the planes. The slip plane should be have a larger distance, and the atomic density of these planes should be higher. A large number of atoms should be present for it to be a slip system. Then we defined about critically resolved shear stresses. What is that? It is a stress beyond which the sample is plastically deforming. And we found the value according from this graph, from this equation and the graphs, which is given by tau CRS is equals to sigma cos phi 1 cos phi 2, above which there is a plastic deformation takes place. So when tau CRSS is taken into account, the sigma will become sigma yield stress of the material. This is for a single crystal. For polycrystal, there will be multiple planes present in the sample, and this multiple planes will be shearing in different directions. That is what we are observing in case of polycrystalline materials. Then finally, we were in the movement of dislocations. They occur by glide, right? But this climb or glide cannot occur independent to each other. They can also not be occurring so smoothly. The climb and glide occur with the help of jogs and kings. First, initially we said there will be motion of dislocations. Then the motion of dislocation takes place by glide or climb. Sorry, and this climb or glide takes place with the help of jogs and kings. More details of how this happens, you can always refer to Professor Shashank's lectures and my previous lectures. Then we defined the king and jog formation in case of a dislocations. So we defined it in a very large, wide scope. Then what is true for a climb process? Fine. Then there is a, as we said that there is a motion of dislocations. That means there is a velocity of dislocations too. And this velocity is given by a tau to the power m, a where a is a constant. And this velocity of dislocation depends on applied stress of the material, purity of the crystal, types of dislocations, and the temperature of the material, temperature at which that moment of dislocation is happening. Then, in the previous class, in the last week of this session, we discussed about the observations of dislocations, how the dislocations will be observed under the microscope or any other things. When we need to observe the dislocations so as to find out how the motion of dislocation takes place, or how are the dislocations present in the material. So to observe that, the first technique was used was etching with NPTEL or some other solutions. Then electron microscopy such as transmission electron microscopy, X-ray diffractions, atomic force microscopy, dark field imaging techniques. More details into this can you can always refer to my last session, a video of my last session. Then we studied about dislocation dynamics, such as internal and external stresses present on the applied to the dislocation, how it will affect the moment of dislocation. It of course follows F equals to ma equation, Newtonian equation, but we need to find out the exact value. Then we found that at a new position of dislocation, the velocity is given by mf to the power x. F is the force applied, where m is a constant. And from this velocity, we can know the position of the dislocation, initial minus final by final, by time, by speed. Yeah. From this velocity, we can find out the distance movement, how it has moved within which frame of time. Then we studied in detail about dislocations in FCC, partial dislocations, how the partial dislocations happen, how the partial dislocations takes place. The partial dislocation should lie on the plane, and the energy after the dissociation should be less. Then only the partial dislocations can take place. And the sum of these Berger vectors of the partial dislocation should equal to the original parent Berger vector. Then we solve this question regarding this. Then what are the forces on a dislocation? These are for screw and edge dislocation. There are different types of forces applied onto the material. But when we add up these forces on the dislocation, it comes out to be positive or repulsive. That means the two defects will repel each other, forming an extended dislocation. And this extended dislocation will be depending upon various factors. We solved questions, and these movement of dislocations, this extended dislocations, they create a stacking fault in a sample. Stacking fault, as you mean, there will be a periodic arrangement of crystals such as ABC, ABC, ABC arrangement. But due to this movement of extended dislocations, the ABC, ABC arrangement is not repeated. There may be some layer which will be absent. This leads to stacking fault energy, which is widely discussed in the for next few slides. Then finally, we discussed about Thomson's tetrahedron. This Thomson's tetrahedron is a graphical model which is only possible in case of FCC, which provides the possible slip planes and the directions, provides the Berger vectors for a slip plane, the line vectors for pure edge and screw dislocations, then the possible partial dislocation Berger vectors and possible dislocation reactions. These are all the informations which are provided by the Thomson's tetrahedron model. But it is only applicable to FCC materials. Then we finally discussed about dislocations in BCC. The active slip planes in a BCC depends upon the composition of the material, crystal orientation, temperature, and strain rate. How it depends upon these factors we discussed in depth in the last lesson. So yeah, this was all about today's discussion. This was all about the whole defects in crystalline solids course. I know I went too fast, but this is just to give you an idea about what we discussed. If you still have questions before the exams, you can always put up in the discussion forum. We'll try to answer the questions. So this was all about today. Thank you so much for attending. Have a nice evening ahead, and all the best for your exams. Hope you can score good marks in your exams too. Thank you.